Hi, another video on process analysis. And for this video, I'll be talking about the flow diagram. Flow diagram is one of the simplest tool that we use to analyze a process. It's basically showing a picture of your process instead of, going to the floor and seeing all this and listening to the people. These are basically important, but however, you come out from the Gemba walk and come back and create your diagram, your chart. And it's basically a picture that show a step by step for the process. Step number one, we get the raw material. Step number two is inspecting the raw material. And step number three is sending the raw material to the line. The line will separate, etc. So it's basically simplifying the process in a one picture and one graph. And this also will show you the relationship between activities, how this is related to each other, if there's any decision needs to be made in the process that would work, that you have to show it. Also, if there is any quality check, you have to show it in the picture. So it's provide a picture that shows the relationship between activities. Typically is shown in the production manufacturing settings. However, it's used in other service industry, and especially in the healthcare. It's applicable anywhere. It's applicable to your home as well. You can show the process step by step on showing how I'm going to do this, how I'm going to understand this complex process. So usually when you have a problem on the floor, sometimes you don't know what the solution. You can't find a solution. You can't find a solution for this issue because you because it's really hard to understand the process. So the flow chart diagram or the process flow diagram will show you the step by step and the relationship, and it is applicable in manufacturing, in production, in service, in healthcare, in information systems, anything. You could use it to simplify things and find a solution. The diagram is used for measuring process performance in units of time and distance, including both horizontal and vertical movement. Assume that moving items requires a time portion to the distance. So now the simple one does not show the time. However, if you could improve it and you add a time, that would be the value stream mapping. It is part of the process flow. What I'm asking you to do, and I think in the discussion, is to do a simple flow chart diagram without need for adding any time. But in the future, once you take the lean class, you will have to work. You could use the flow chart diagram, add some times. You do time studies, you add the time, and you include it into the value stream mapping. This is what we call the VSM, the value stream map. Also can be used in conjunction with the process activity chart. And this is the process activity chart. It's something that I did skip it here because I want to focus into the symbol one, but here's the general process chart. Will show you the activity. Activity number one, it's the number five is the operations. Activity number three is inspections. Transportation is 10. Storage 0. Delays is 7. And this is showing you the time needed, the percentage. And once you redesign the process, once you do the improvement, you could put down what you have improved, what's in your mind, or maybe you tried it, and then you show the difference for the improvement. So my opinion, for any process improvement, it starts with a simple flow chart, and then you improve it. You add more time to it. You go to the value stream map. You show the times, and there is something called a current value stream map and future value stream map. And this is showing you what the current state for your current process and what would be the to be process, how the process will look like. And this is something similar. So I want you to skip this part. However, I did explain it a little bit. So here's the activities. This is the current process, the future or to be process. And last, the blue column is the difference, what's improvement you have done between the current and the future or to be, or what we called here in this slide, the redesign process. Okay, again, just to keep you in a symbol, stick with the symbol one, which includes just the shapes, something like this. So before you redesign a process, you will see in a process like this, you get lost, you don't understand anything. However, one of the goals for process improvement and process analysis is to simplify things and showing how the things go from one to another. Okay, what I want to do here, I want to show you some symbol, uh, uh, the symbols that we use, symbols that we use in any process. So whenever we have a work in progress, we use this triangle. The flow of material we use an arrow, and processing step would be triangle. Decision point would be this diamond point. So before I go ahead and continue with this, what I want to do is share with you an activity that I put it on the discussion here. I put it on the discussion here. All right, so I'm going to share this one here. And so this is from discussion 2, and I did have put some video on glass bottles making factory, and I did provide an optional reading material. And in here you will see an example of making a sandwich here. So what you will see the four activities for the process. You have the input, you have the process itself, the transformation activities, you have the output, and there is a feedback in here. So if you go from the input here, this is where you start. You go, you have the bread, you have the butter, and then you insert the bread into the toaster. You depress the toaster lever, you remove the toast, you add the butter. Here's where you add the butter here into the toast, and this will be the complete product, the complete sandwich. And then you go to inspection here. You want to go inspection. Is it good? If yes, go and enjoy it, and that's the end of the process. If no, go try doing it again. And maybe you could add some decisions here into the remove the toast. You could add here another decision point, a diamond shape, saying, is the bread toasted the right level? Is it gold enough for you? Or maybe it's black. If yes, you move on to the next phase. If no, you're gonna go back to the previous phase and do the process again. So this is just an example to show you what the symbol flowchart will look like. And this is very helpful because it will show you how would you find room for improvement in the process. It will give you a simplified ways to understand the process, just looking into one graph, one chart, and you will be able to understand. You don't need anybody to explain it to you. So you need to make sure this is clear and all the details included. All right, now we're moving into the performance measures. The performance measures, these are the measures that we use to measure the performance of a task. So assume a process in a place. What do we need to measure in order to understand how efficient it is? Okay, in order to make sure a decision about efficiency, we need to know exactly how many units we have. Or maybe some people would say, let's take a look into the waste time, which is what we call the non-value added versus the value added time. And these kind of the efficiency. Maybe there is another way for doing it. Also, there is another way for doing the performance measure, which is the capacity. How many units? This is basically how many units per unit per time that will go through this task. Maybe this is just, we divide the system into subtasks, and you divide you study the task individually, and then you put them together as a whole system. All right, so again, what is the capacity? It's how many units you could do per time. So I could do, two units per hour. So this is what the capacity of my factory is. I could serve three customers in 5 minutes. Maybe if you have a fast food uh, restaurant, you could measure your capacity with this. So based on this, how many based on the three customers every 5 minutes, you could identify what's your capacity, how many customers you could serve per day. You could say, okay, well, I have a 12 hours shift, and you could do the calculation to find how many customers you could serve per day. Uh, Another things that we keep an eye on is the bottleneck, and basically what the process that limits the system from producing or serving. There is, in any system, there is a bottleneck that will prevent you from moving forward. So imagine that you have, let's see, there should be an example here about the bottleneck. We'll come up to an example in just a second here, but it's the step, the task that will prevent the system from serving more customers, from producing more items. The bottleneck is basically the slowest step, the slowest task in the system. Throughput time, how long does it take to go through the system from X to Y, from A to Z? We need to find out what would be the throughput time. So now you will get confused with a cycle time. The cycle time, it's just the time that you need in a process, but the throughput time, including the wait time as well. So there is a slight difference between throughput time and the cycle time. The cycle time is just the processing time. How long it will take you to process the one unit to get out of this machine. However, maybe after getting out of the machine, there could be a waiting time where to go to the second phase, the next machine, there will be another 5 or 10 minutes. So the cycle time does not consider the wait time. However, the throughput time to go through the system from raw material to a finished product or finished service, that's what we call the throughput time. How long does it take to get through the system? All right. Capacity of task is the physical limitation in terms of how much can be processed in this task. The cycle time, what is the cycle time? Average time for completion of a unit at a production step or process. Does not include the waiting time. So the cycle time does not include the waiting time. However, the throughput time is including the wait time. And this is measured as time per unit. So 2 units per minute, for example. Throughput rate, average number of units processed over a time interval, measured as a unit per time. So the throughput rate is measured by units, how many units we could finish in 1 hour. However, the cycle time, how long will take you to process 1 unit. The throughput rate would be 1 over the cycle time. This is what we call the throughput rate. And this is equal to the capacity. So in order to find the capacity, you could find the throughput rate. And in order to find the throughput rate, you have to divide 1 over the cycle time. And the cycle time would be how long it will take you to finish 1 unit. So I need 2 minutes per one unit. So this is what we call the cycle time. There is some key relationship here. Computing the cycle time, here's an example. Producing 100 cars on average, production task 5 hours per car. It takes 50 hours to set up the production line. So the cycle time would be the setup time plus the batch size times the time per unit divided by the batch cycle or the batch size. So if we say 5 hours, 50 hours the setup time. So let's see if we could do the 10 here. Okay, that would be 50 the setup time. Each car will take us 5 hours. We have the batch is 100 cars. Make sure to use the parentheses. especially if using Excel, divided by 100. If we do the calculator here, the calculator would be 5 times 100, that would be 500, plus the 50, the setup time, that will be distributed by all, divided by the 100 cars. So each car will take 5.5 hours as a cycle time. We did not consider the wait time. There could be a wait time. This is something else we call the throughput time. All right, computing the cycle time, setup time is 15 minutes, production time is 25 minutes. What is the cycle time between points A and B of the process if we work on a batch of 10? Same thing, what you want to do is 15, that's the setup time, plus 10 times 25. Divide that by 10. And make sure to have the parentheses again, one here and one here and one here. Okay, using the calculator here, I'll see if we can find the calculator. Okay, again, 25 per unit. So we have 10, so 250 plus the 15. That'll give you a total of 265. Divide that by 10. 26.5 minutes per unit. 26.5 per unit. That would be the cycle time. All right, now the bottleneck. The bottleneck is the process stage which the smallest throughput, the longest cycle time. So if we look into which task is the bottleneck, look at the unit that produced the less units, the smallest throughput rate. You will see this is 2 units per hour. They produce very little. And what's the result of the bottleneck? It will slow you down. So in order to do like a 3 or 5 units, you could only do 2. You stuck with this number. So the capacity of your line for this one is the capacity of your bottleneck. So improving the bottleneck. So imagine this is, okay, we have a 2 units per hour because we are we have an old machine here. If we reduce this to a better machine with a better like, let's say 5 units, so now this would not improve it to 5 because we have another bottleneck here. What we have to do, we have also to replace this machine to have another capacity of 5. In this case, we improved the throughput of the whole line. So let's go back to the bottleneck. What is the bottleneck? Is the slowest unit. And as you look into this line, the 2 units per hour is the slowest one. And this will prevent me from doing more. So this is the bottleneck. So when I create the flow chart diagram, and I know this task in particular, this machine in particular, they're producing only 2 units, then I would say, oh, okay, well, stop right there. Here's the problem. We're not producing enough because of this bottleneck. And basically what's going to happen here, build up more work in progress inventory. Work in progress is not needed. This is a bad inventory. We're not needed it. We don't need the process, work in progress. So the bottleneck is this one right here. So what we should do from continuous improvement perspective is you need to investigate, why is this bottleneck? Do you need more workers? Do you need a newer machine? Is there an inspection needed before this? Or what exactly happening in order to remove this bottleneck? Your goal is removing the bottleneck. All right, so what's the capacity of this process? The capacity is 2 units per hour. You cannot do more because this is only, will handle only 2 units per hour. The capacity of the process is the minimum throughput rate at any of the stages. So this is the bottleneck. We know this is the capacity is similar to the bottleneck. So we cannot produce more than 2 units per hour. All right, throughput is the average time until it takes to go through the entire process from A to Z. This is including the wait time, and this is measured as the time. The work in progress is the average number of units in the system over a time interval measured in units. The throughput time would be the work in progress divided by the throughput rate. And this is what we call it, the Little's Law. This is a worth to investigate and look into more details about the Little's Law. But it's basically the work in progress calculation, and we'll show you what would be the throughput time using the work in progress and the throughput rate, or you could change the equation to find out what would be the work in progress by multiplying the throughput rate by the throughput time, and you will find what would be the work in progress. And this is, again, we call it the Little's Law. It's an important concept in operations management. Look into this Little's Law, and if you're interested to know more about it. But let's go back to throughput. Is the average time to go through the system, including the wait time, and measured by time. The work in progress is the number of units in the system that is not processed. If you remember, we said here, because if this is slow, because this unit slowing the process down, what going to end up is work in progress. So there should be this work in progress should be removed, and work in progress is not good in your system. You should remove any work in progress. All right, how do we analyze a complex process? There are simplified with these 4 steps. Look at the process step by step, this is what we call it again, flow chart diagram. This is how we look into the process step by step. We need to look into the flow chart diagram, because that will help us to give a better understand the system, and will show us step by step. Determine the throughput rate. We need to find out sometimes. Let's take a look into the capacity and the throughput rate for each system. If there's any bottleneck, we should identify the bottleneck rates. That's the smallest processing rate, the one that slow us in the system. Number 4, the capacity of the process is equal to the capacity of the bottleneck. We know that you cannot exceed the bottleneck capacity, because all the parts, all the process has to go through the bottleneck, and the bottleneck is not doing any good. They're slowing us down. So your system capacity will be the bottleneck capacity. All right, let's take a look into this example. We have 2 machines machining, and there's looks like there's a work in progress, there's an assembly, there's another work in progress, there is a pack and ship. Let's read the description. Work begins at the machining center. Here 2 lines from the heads of the hammers and place them in a buffer. Handles are attached at the assembly step. Number 3 is finished hammer are sent to the next stage, where they are packed and shipped. Yeah, here's the process data, which is what we're looking for. Machining setup time is 80 minutes. Cycle time is 4 minutes per unit. Processing patch size 1200. Identical lines, we have 2 identical lines. Assembly manual by 2 workers. We have 2 workers here. No setup needed. Each hammer requires 40 minutes processing. We have 24 workers, but again, there has to be 2 workers, so 17 basically. We're talking about 17 workers here. Back and ship to 30 minutes setup time, 2 minutes per unit processing, load size of 100. All right, let's take a look into the step 1, the machining. We're going to take a look into one line. So for one line, we need 200 units. This is what's the batch or the lot size. We have a setup time of 80. Again, this is taken from here. This is the 80 setup time, plus 200 times 4, which is the cycle time. We need to know that we can do For the 200 units, we can finish them in 880 minutes. This is how much time we need to process these 200 units. So if we need to find out, this is a totally separate calculation. So if we need to do the throughput rate, we need to find out how long will take us to produce one, how many units per minute. You divide the 200 units by the total time that you need. So that would be the 2.227 units per minute, or 13.63 units per hour. So if you see now, some people, they will get confused why we did this. Well, first of all, we did not consider any wait time here. So in real life, you will see some wait time. So you should add that. So if there is another wait time of, let's say 1 minute. So you want to add another 200 minutes as a wait time, So now what we have, this is called a cycle time. Throughput time would be, adding these together would be 1080. Again, this is throughput time. So for the throughput rate, you will not use the 880, but because we don't have a wait time here, we use the 880. So you divide 200 by the total time, and this will show you what would be the throughput rate, which is basically 13 units per hour. So you could round it down, saying you can't have 13 and a half, for example, or 13.6. You could say 13 units per hour. This is what you could do. So since we already have two lines, so this is only for one line. So what would be the capacity if we have two lines? 2 times the 13.63, that will give you 27 units per hour for the two lines. So this is for the machining. We know that we can produce 27 units per hour. If we know that we're working in a shift of 8, you multiply this by 8, and you will find out what would be the capacity per shift, if you need it. All right, now let's go to the assembly line. We have 1 unit requires 40 minutes. 1 unit requires 40 minutes of processing time. So the throughput rate is 1 unit per 40 minutes. That would be equal to 0.025 units per minute, or equal to 1.5 units per hour. We have 34 workers, however, but we need 2 workers to work on 1 assembly. So that would be 17 times 1.5. That would be 25.5 units per hour. All right, so again, for the assembly, let's go back to the information. Assembly, we have 2 workers on a 1 job, requires 40 minutes assembling. Okay, 40 minutes to assemble the 1 unit. 1 unit will takes 40 minutes. So we can do 1.5 units per hour. All right, so now we know that for this lot, we will require about 25.5 units per hour. We have from before 27 for machining. So 27 plus 25, this is what we have so far. Now let's go to the pack and ship. Pack and ship would be a setup time of 30 minutes. We have a lot of 100 units. Is it 100 or 200s here? Okay, let's see. Okay, yep, lot size is 100. It's right here. This is what's the lot size in the packaging. So we have 30 setup time. We have 100. That's the lot size times 2 minutes. 2 minutes per unit. That would be 230 minutes per 100 units. And so if we find what would be the capacity or the throughput rate, would be 100 divided by 230. So that would give you 26 units per hour, 26 units per hour that we can do the capacity. All right, so as a summary, this is what we have. The process, what is the capacity for this system? We have 27, 25, and 26. And the assembly here is the bottleneck because it's slowing down the process, not by much, but the system capacity would be 25 units per hour. So you cannot exceed that. Even the machining can do 27 or the packaging can do 26. However, because of the assembly is slowing you, you cannot produce more than, you cannot serve more than 25. All right, so another things that we need to talk about it is the buffering. Sometimes some of the terms that we use when we do a process analysis is buffering. The buffering is something between the process. So imagine this is a process A, okay, and this is process B. All right, so if sometimes we put some buffer in between them, and there are so many advantage for doing this. First of all, we need to prevent a process from starving. And why is that? Because as long as the machine is working, you don't want to underutilize this machine and shut it down because of there's no enough input to that machine. There's no feeding for that machine. So the buffer is important. It's a small storage area between the processes. It's a small storage area between the processes, and this will keep the machine moving. It will not let the process starving. It will make it more efficient, more utilization. It will cut down the non-value added time. So it is one of the key aspects that we use. The buffering is important. Is the work in progress buffering? I would say no. The work in progress is happened because, not because you need it there. It happened because you cannot process it. But the buffer is needed there. You created that area. You put some raw material in the buffer in the storage. Let's think about a basket, a small basket that you put some screws in it. These are buffer. So, and this is important because you don't want the operator for that to run out of screws and go back all the way to the storage area, the main storage area to get these screws. What you could do, you could feed that process, you could feed that operator with screws in a small basket. However, the work in progress is totally different. It happened against you. It happened because you can't process it. It happened because you have a bottleneck. But for the buffering, it's something that we solve it to prevent process from starving, lack of material. And there's another term called blocking, stoppage of workflow because there's no storage places. And this is basically what would be the typical place where you need some buffer here. You need to create a buffer to prevent any starving and you keep the process going. All right, with that said, I'm going to end up right here. I hope this is helpful. Please feel free to ask me questions. Now there's one more video that I will be making about the break-even point, and I will be providing you with a more example on the break-even point, the revenue, the cost equalization point, etc. With that said, I'll see you in another video. See ya.